Everybody usually starts here with thank you, Samson. I'm just going to say that I hate those. You fucked up my opening. How can I get the laptop? Yeah, right. That's it. So I also started with some pictures exactly the same. That's a picture of 2009. The same picture if you saw in Alex 2013. Actually, there's 13 people missing, by the way. This is just something to say about the kind of total lack of discipline in this group. It's very stupid. I'm just repeating the joke. Like one thing we learn is a finite amount of jokes in this universe. So we make it classical and then we do stupid. So, okay, my picture of the joke is what is Samson thinking? Oh shit, I don't know. Oh wait, let me do it. There. Okay. That's better, isn't it? I win. So this was actually what was supposed to be the cover of the volume, but these stupid publishers, they're all stupid of course, they sort of didn't want a picture of a person on the front of the volume. Bit stupid, so they just cut out these 3 small pictures. But I think this one is nice. You agree? I win again. Okay. Right, so my talk today is actually about, it's called the logic of quantum mechanics, so it sounds a little bit like the physics stuff, but the main focus will be on the analogy of structures which we've heard quite a bit about now. And Samson and I started to sort of lay down for describing quantum mechanics and a totally different area, which is actually meaning in natural language. And so my talk is really about how exactly the same structures occur in both fields. So let's start with a little bit of history. So in 1932, von Neumann formalized quantum mechanics in his book. 1935, the idea of I would like to make a confession which may seem immoral. I do not believe in Hilbert space no more. 1936, the so-called quantum logic came about. It all failed. I'm doing this quickly because I've shown this slide like about 500 times. So okay, failed revolution, quantum logic. Why? So the deep fundamental question is, why do we use all the Hilbert space stuff when we formulate quantum mechanics? Like, why do we use complex numbers? Why do we use continuum even? Because some people think that space-time is discrete. Why vector space? Natural language people use vector space because just the brute hammer with which you can do everything. And why do you use the inner product? So, okay, why? Von Neumann's answer, he used it because it was available. No deep reason whatsoever. So, okay, let's see the physics. So the reason von Neumann actually crafted the work of this quantum logic because they really want to capture the notion of superposition. So they formulate this property of a physical system as a lattice, and this lattice was a Boolean. And the idea is if you don't have a distributive law, then actually you create superpositions, because if you make a join of 2 things, some other thing may sneak in, and that's exactly your superposition states. So that was what they tried to capture with their non-distributive lattices. But at the same time, Schrödinger said the stuff, which is true so of quantum theory, is how systems compose. Funnily enough, physicists, compositionality is still not a word they know. They don't know it. They don't know about this, but Schrödinger wrote about it. Although, on the other hand, if you look at quantum computer science, whatever people in quantum information have been doing, they clearly agree, because all the new phenomena which were discovered like in the last 20 years was really by embracing the idea that you want to start with composite systems. On the other hand, the death of quantum logic was a failure to describe composite system in a sort of conceptual way. Right, so although people have embraced this idea, there's, from an axiomatic perspective, nobody really ever started to formulate quantum mechanics, like taking composition serious from the start. That's more or less what we did in 2004, like just start by taking composition serious. So the game plan, okay, so you want to solve the following equation. You want to get rid of all this other stuff of Hilbert space, and you just want to retain the tensor product structure without continuum, without complex numbers, without anything. So how do you do that? That's the first question to solve. It's question C0 because it's already solved. Because you want to axiomatize the tensor without reference to spaces, which means you start with a symmetric monoid category. simple as that. So nothing else. Here is a different question, which is more of a conceptual nature. Like, what sort of assumptions do you need to add here to this tensor? This tensor just means composition, to actually reproduce physical phenomena. So what are the sort of actions you put on a tensor to reproduce physical phenomena? So the clear analogy is, do you want, for example, a Cartesian structure? Of course you don't, because you have something like quantum entanglement. So you definitely don't want a Cartesian structure. What do you want instead? So the sort of more crazy question then is to investigate whether whatever structure you come up with here to describe quantum physics maybe will be useful for something else. Might be totally different, and then it will teach you something about the sort of overarching logics of a field like quantum physics and maybe some other field. Okay, so those are the questions. Okay, answers. Like I say, question 1, answer the symmetric monoidal category. So this program has started, and then some philosopher of physics sort of said that this approach, as opposed to many other mathematical approaches, like what you got was a sheer ratio of results to assumptions. You hardly have to assume anything on top of your symmetric monoidal structure, and you get tons of stuff out of it. So this means that you're probing something very essential. It's for computer science, it's something stupid. It's like just starting composition a little bit. In physics, it's like a big deal. So another nice thing is, I'm now contrasting, for example, with Birkhoff von Neumann and many other axiomatic approaches that in very short term, sort of this approach actually helps you solve many open problems even in mainstream quantum computing. I mean, referring to one paper by Ross and Simon in 2010 in Ireland, where they solved some problem which was open for a bunch of years in quantum computing, just using this sort of method, the compositional diagrammatic way of rewriting. And okay, the really nice selling point of the whole thing is that you actually get a simple, intuitive diagrammatic language. And the difficulty is that you don't want to mention the word category theory when you're trying to sell this to physicists. So you want to sell this without actually telling them that there is some horrible, whatever, abstract nonsense mathematics going on behind the scene. So you have to give it a new word, like I call this pictorialism because it sounds stupid, and then you get people actually, Lucian actually should have been here, but he couldn't come. So people say, this Lucian is notoriously anti-mathematical. He hates maths. It's kind of very funny. He hates form, he hates maths, but because it's diagrams, he kind of likes it. It's anyway. So this is the way to solve these things to physicists. And okay, I write down 3 pictures here. So this is actually in relation to my second question. So okay, so this is derivation of physical phenomena. Was Samson or Rick's 2004 paper which started this approach. Here you see another paper which is with Steve Clark in Cambridge and Maroon in the back, which is about the meaning in natural language. Looks exactly the same. I'm not going to talk about this today, but again, another diagram which is about like page updating and things like that in probabilistic reasoning. Looks exactly the same again. It looks slightly different because you see some Frobenius over here, but the punchline of my talk is that the same Frobenius also is going to come in here and here too. So, but anyways, so you see 3 completely different things. This is like sort of probabilistic reasoning, probabilistic inference, meaning in natural language, behavior of matter. All the same language. Right. Yeah. The logic of it. So why do I call this the logic of quantum mechanics? And the first thing you have to answer there is, what do you actually mean by logic? Because one of the big problems when people are doing quantum logic, oh no, this is the true logic of nature. Oh no, this is the true logic of nature. What the fuck is logic of nature? What does it even mean? The logic of nature. I don't know what the logic of nature means. Okay, so what is logic historically? Logic is structure in language. I think that's fair to say. Boolean algebra comes from the use of the word and or and if then and stuff like that in language. Yeah? That's something you try to formulate. The Greeks were trying to do that. They formulate sort of logical content in language. And okay, like give an example. Alice and Bob ate everything or nothing, then got sick. So you can formulate, because if you eat everything, you get sick because you eat too much. If you eat nothing, you starve. So you get sick. So anyway, so you can formulate this logically. Now, another pragmatic option is logic lets machine reason, and that's more or less exactly the sort of stuff Alex was talking about. Now this diagrammatic languages are used to try to get some automated reasoning to work, and therefore we're stealing a lot of technology. Well, he's stealing a lot of technology. He's stealing a lot of technology from Edinburgh, and then we built this group who have this sort of kinky thing, theory mind, you may have heard about. So a lot of this theory mind technology is now being stolen and incorporated in this sort of diagrammatic software. Right. So now here's the claim to say that why the arrogance of cognitive the logic of cognitive take two is that we appeal to both senses of logic, the one in natural language and the one in automated reasoning. We hear about the automated reasoning thing in Alex's interest, and then the other thing is the second thing I'm going to talk about. It's how actually some problem in natural language, some open problem in natural language processing sort of got solved by using these diagrammatic languages. This will be the last part of my talk. Okay, anyway, Alex will already show this automatic side. Okay, let's start with the word Samson 90 in 2004. This is Simon's book. Simon here? Okay. Right. So the basic idea is that you start with boxes and you think of inputs as input wires and output wires, and whatever system you want to think about, whatever process you have, this is the way you think about it. You've got systems which you represent by wires, you've got boxes which you represent by processes. This goes for what Dan Gika was talking about, this goes for physics, obviously, this goes for computational processes. As we see, this even goes for linguistic processes. A nice thing is that implicitly, the whole idea of the idea of composition of systems is built in, because if you write one wire, it's one system, if you write n wires, it's n systems, if you write no wire, it's no system, which is sometimes you don't care about some input system, like when you do a preparation or something, so all these things are automatically built in. We got ways of composing these processes. I give 3 names because that's actually sort of kind of, you could say, sequential, which is sort of computational approach. Causal, because in a way G happens after F. Connected, because you're really topologically connecting these things. And you've got a parallel composition called acausal, because they are sort of spatially separated. Disconnected, because you don't connect them. And these are your logical connectors. And it's well known that by representing things diagrammatically, you're not just using a new notation, but non-trivial equations, like here, bivectoriality becomes trivial if you write it down diagrammatically. And so here we can make a big claim, and how should I say this? So if you look at all the equations of a symmetric monoidal structure, of course bivectoriality goes if you do diagrammatically, because of the argument I give you here. You write this down diagrammatically, you get this. You write this down, you get this, and you get a tautology. Same is true, like for example, for associativity, naturality of associativity. Okay, so I've got 3 processes. It's not very good. Not very good. Okay, that's better. F, G, H. Okay, 3 processes. Let's put some brackets. Okay. Here I got 3 physical things. I got a curve, I got a total, and I got a. Where are the brackets? I don't see the brackets. Where are the brackets? They're not here. Brackets are unreal, you know? All the stuff you have to do in category theory, like naturalized morphisms, to actually say that essentially putting these brackets or these brackets, that's just syntactical garbage, which is a consequence of using the wrong stuff to describe your things. Or in nature, the wrong stuff being like set theory-based mathematics. It's just wrong, it's just physically wrong.
Aren't the brackets the order in which you put the things down on the table?
Well, you may do so, but if they're here, there are no brackets.
Once they're done.
You could give meaning to that, but that's what a programmer would do. I would take this variable, this is not about programming. These things are here, they're here.
Sometimes there are brackets in mathematics too, which is like in Taishura.
Of course, no. I'm saying the problem is the brackets are not in physics. So the physical categories are simple strict categories which are no equations, which are totally trivial and which are all the those described by diagrammatic language. That's my claim. it's much easier to sell this than all the whatever coherent stuff you have to sell otherwise to people who don't like maths. I talk to people who don't like maths. So this is basically symmetric model category. We can go a step further. We want now to go to a level that we can actually do some physics. And I write a quantitative metric is because I want to introduce an involution, which is basically if you've got boxes, then you can flip the boxes upside down. That's a piece of structure which I'm introducing. You can flip a box upside down. It's obviously an involution because if you do it twice, you're back where you started, right? Now, the key idea, like going back to Schrödinger, is that we want to articulate in a constructive way that quantum systems, when they come in pairs, behave different than classical systems. So how do you do that? Well, basically you want to say that something is manifestly not Cartesian. Cartesian would mean that giving a description of the whole is the same as giving a description of the parts. So you want to say, no, we're not doing that. How do you do this in like a manifest constructive way? Well, basically you say that you can't split this thing up in two because you're basically going to connect them. You're going to connect them. You put a wire between the two. Then you cannot split it in two. So you use this paradigm like the topology is everything which matters. So you introduce a wire and as some sort of informative hand-waving rule, only topology matters. Huh? It's sort of an intuitive thing which you do. And then as a consequence, you get an equation like this, which algebraically is really what you take as a starting point. This is like what gives you the compact closure. But it's basically just saying only the topology matters. Okay, from there on, you can start to do some algebra. You define what is a transpose. So here we've got a box. We're sticking a wire here, we're sticking a wire there. And we denote the whole by just doing a 180 degree rotation. We call it transpose. As it turns out, if this is so-called Bell state, then this is effectively the linear algebraic transpose. Similarly, you define conjugate just with starting with the flipped box from what you start with now. And then you do a bit of tautology. Okay, this is tautology because I can take this box, just slide it around here, which is actually just unfolding the definition of transposition. So you take this box, you slide it around. You take this bit of wire, you yank it, then you define such a box to be such that if you compose it with the flipped one, it vanishes. You get this. Okay, we introduce Alice and Bob, and this is quantum teleportation. So that's sort of the, and then like from this perspective, it's very trivial, of course. Like one has to realize that quantum teleportation was something people came up with in physics in 1992 or 93. So this was more than 60 years after von Neumann's formulation of quantum mechanics. While here it's a totally trivial thing. Right. Some hardcore math results. So there's some serious math behind the scenes. So, okay, like this is just the coherence result for what are now called Dagger compact categories. So an equation in between Dagger compact category language, rolled and even though it's derived from the graphical language, it's just coherent. And there's like a very nice theorem which actually started with Gordon, and this was for traced monoidal categories, but then Salinger extended this to Dagger compact categories. And the equation statement between expressions in Dagger compact categorical language holds even though it's derivable in Dagger compact category of finite dimensional Hilbert spaces. Putting those two together says that, I'm going to put it informally, any equational statement in physics which involves those concepts, states, operations, effects, unitarity, adjoints, projection, blah blah blah, can be derived in Hilbert space if it can be derived diagrammatically. That's the result of these two. If you sort of chain these two theorems, then you actually know that you've got a diagrammatic language which allows you to prove any equational statement of this sort, even though it holds in Hilbert space, meaning it's through quantum mechanics. There are some little caveats there which have to do with that you have to prove it for every dimension, not for a single dimension. But, okay, anyway. Important. Skipping this. And now something completely different. So we're going to use almost the same language for a problem in natural language. This is like I said, joint work with Steve Clark, Cambridge Computer Science MLUs, now we know Queen Mary. Okay, a process, a completely different process than a physical process or a computational process. So the from words to a sentence process. What does this mean? You consider the meaning of a bunch of words, which, like for us, mean, you look them up in a dictionary and you see what they mean. That's for us what meaning means. We open a dictionary, we see what a word means. Yeah, that's funny. You don't do that.
No, it's a very refreshing philosophy.
Okay. But so, in natural language process, the meaning of a word is actually a vector in a vector space. The way it goes is like one takes like 1 million of context vectors, and then one takes a big corpus and one looks how many times a certain word appears in the context of these context vectors. This gives you relative frequencies, and this then sort of combination of all the relative frequencies gives you a representation of the meaning of that particular word. And now, for example, if two words are synonymous, you expect them to appear in the context more or less interchangeably, so they would have the same representing vectors. So if you then compute in a product, you expect these two vectors to be close and this inner product to be high, so you get a high measure of similarity just by computing. You get a measure of similarity just by computing in the product. So that's how people work in natural language processing, and you can imagine that maybe this is what happens behind the scene with types of words in Google, and it gives you some outputs for your search. Now, what is the meaning of a sentence? What is the meaning of a sentence? We don't look sentences up in dictionaries. If you don't know, if somebody tells you a sentence and you never hear it before, you don't look it up in the dictionary. Usually you understand what it means if you know the words. How does this work? So there is some process, which is the from words to sentence process, which sort of takes meaning of words, produces it in a sentence, and we are able to do this thing. We are able to do this thing. So how do machines do this? Well, that was sort of an open problem. If you get the meaning of the words as in vectors or something like that, is there an algorithm to produce the meaning of a sentence from it? Or first of all, how would you even represent the meaning of a sentence? What should it be? Should it also be a vector, whatever? Now, definitely something which plays a role there is grammar, because grammar is, if your sentence if this would not be a sentence, if this would just be a bunch of words with no connection to each other, typically it wouldn't mean anything. So this should be grammatically well typed to actually get the meaning of a sentence. And so if you look at the community of people who are interested in language, there was like this big separation between those who were doing grammar, like Chomsky style, Lombeck style grammars, and those who were actually doing the more pragmatic, probabilistic work like in using like distributional models and vector spaces. And basically what this work did was sort of combining the two in one approach. How does it work? So I'm using the same representation as I used before. Like if you think of a verb, like Alice hates Bob or something like that, then the verb hate is basically waiting for an object, Alice, and subject, Bob, to actually give the meaning that Alice hates Bob. That's how it works. And clearly, we're again in a situation like we started earlier, that such a verb, like now, these wires in terms of physics, they meant 3 physical systems. Now they sort of, these wires means like, what are the type of things which are interacting? You know, there's an object interacting, there's a verb subject interaction, and then there's like the meaning of a sentence, which is spiral. Now, you don't want the meaning of the sentence to be independent of the object and the subject, right? You don't. Because otherwise, if Alice hates Bob, which she probably has very good reasons for, then anybody would hate anybody. Because the meaning of the sentence will not depend on the meaning of the object and the meaning of the subject, if they would be separate. So obviously we're back in a situation where you've got this strong entanglement, and then, oh, there's another birthday boy. Yes, Lombeck, 90. So, yeah, some people here, this is not the only festive I'm doing, I'm also doing one for this kind of Michael?
Not yet.
Phil. Okay. So this is not what you find in Lambick's paper of 99, but this is what it means. So you know, there is Lambick calculus, then he came up with pregroup. This is actually what a pregroup is. So it's very similar to the sort of equations you saw in a couple of talks now, with the main difference that we're not talking about a symmetric structure here. We're really talking about something non-commutative. Obviously, the order of words in the sentence is kind of key to the meaning, right? So you're dealing with something which is non-symmetric. Now, I'm not going to go into detail, but so this is basically grammar. This is grammar. This is what grammar is. And how does this work? It works completely analogy to what you know, maybe Lambick grammar. So I was talking about a verb. A verb produces a sentence, which I denote by S, if I get a noun on the left and a noun on the right. So you've got something waiting on the left for a noun, something waiting on the right. And so this is like a left inverse and a right inverse, and you can do a bit of algebra. So here you've got your verb, waiting on the left for a noun, waiting on the right for a noun, produces a sentence. Right, now we're going to write this dynamically. That's something people know in computer science too. So here you got the verb, the sentence goes through, and the noun annihilates with the thing which is waiting for the noun. It sort of annihilates, like in a physics and annihilation thing. Oops. So you can see the dynamics from a noun, a verb, and a noun, you get a sentence. And it's just a matter. And this is basically the algorithm. This is the algorithm. You take the vector of a noun, you take the vector of a verb, you take the vector of the noun, and this process here, which is a linear map, this is like an identity, this is the adjoint of like a compact structure in your vector space. This is a linear map which transforms the values of these vectors into the meaning of a sentence. So you get an algorithm to compute meaning of sentence from meaning of words. Right. Just like as a conceptual, how much time do I have? 3, 4, 5 minutes?
How much you want to take off people from chat?
What? No, but exactly. Yeah. After when did I start?
Let's
3 minutes.
3
Okay?
minutes.
No,
Let's go
perfect.
for 3 minutes.
3 minutes is perfect. So here is a little bit of a logical sentence. Like you got words like Alice, like, Bob, words like not words like those. Right. So words like this you would get vectors from some corpus by some empirical means. So what do you do with something like does and not? Well, does nothing. So you just stick in a bunch of wires. So the top bit, like the top bit of the picture is what you get from like grammatical structure. You just open Lambick's book and you get this bit about this to do with the grammatical structure of the sentence. Not doesn't really do much, but it's sort of some sort of negation going on, right? So you put some box of not, and then you just do the sort of wire algebra, which means you just follow the wires. You got your like here, Bob comes in, you got your like here, Alice comes in, and then what goes out, something goes through not, goes out, so you get this, and then if you want to, and you use some transposition, then you get that the meaning of Alice doesn't like Bob is basically Alice, Bob, like not, of course. That's, it follows. And then at, is that here? At in the news, then, oh, sorry. They did a bunch of experiments I don't understand anything about, but so they did better than anybody else. So they win. Right. And so I'll stop with, so where does the analogy stop? Where does the analogy stop? We heard a lot about Frobenius algebras today. We have been using Frobenius algebras a lot, like Jamie was and Alex were already mentioning these spiders which we use to represent classical data or observables. So actually I should say that when Dushko and I started doing that, I know no maths because I hate maths. Should be clear, I don't know maths. So just reverse engineering some equations, and then Gordon was asleep just now. Actually said, "Hey, that's a Frobenius algebra." Somewhere in past. Yeah, he said that in my sleep. Anyway, so anyway, so that's what we use, and the main thing is like a theorem which says that these structures, if you sort of implement, if you look at the category of Hilbert spaces and the spiders, they're exactly orthonormal bases. So this is a theorem with Dushko and Jamie. So, okay, you can use these things to, in a compositional way, represent classical data. And then this is what we saw in dense start, exactly, dense start. This was the fork, and this was XOR, and they form a pi-algebra. So it turns out that if you got complementary quantum observable, which is sort of the strongest way of being incompatible, they exactly obey the same law. And Miriam, I don't know whether Miriam is here. Miriam actually showed that for an important fragment of quantum mechanics, this diagrammatic calculus is again complete. So everything you can prove in Euro space, you can prove diagrammatically. So we got again a completeness result for this sort of multicolor calculus. I don't think that's anywhere available, that paper, right?
I don't think so.
Shame on you. Okay, and then, so we use this also to model like the different sort of entanglements, and which is kind of nice because like usually you have the spider, a lot of spiders fusing together. Turns out for some different kind of entanglement you got exploding spiders. If two spiders meet each other, they just fly to pieces, and that's sort of interesting maths. You can make Hollywood movies with that, with Van Damme and stuff like that. Now, actually, this was my final punchline. Like, this is some work which we just got again with Ruud and Steve, which we just got accepted for some conference. I don't know what even the name of the conference means. MOL. Models of Language. Mathematics of Language. And I'm not going to explain this, but you see again the forbidden is also showing up, and this is in modeling relative pronouns. So this would be a sentence like the man who Alice hates. So basically the man who Alice hates, you should solve this with the right vectors, and the answer should be Bob. So this is like an equation, you can solve this. The man who Alice hates, and you compute this, and you get Bob. Wow. Okay, thank you.
Questions? Yeah. Everybody isn't already stunned.
Just to show back away. So usually, oh no, go to the last one. So usually you have to parse, but here you don't have to parse, but you have to put in extra lines. So where do the extra lines come from? Like how do you know the two S's have to have a line between them?
You mean this bit?
Yeah, for example.
This is the grammatical structure.
So you have to parse.
So yeah, this is you take the parse, you use the grammatical structure. From the grammatical structure, you get sort of the cup and the cap structure.
Yeah,
It's just a different way to write down the grammatical types.
yeah, so why do you need the cap structure? It's all enclosed together.
Well, you actually only need one for the grammar. You only need one of the two. But if you want to, so the other ones become useful if you want to sort of model logical, well, I don't know, like words like thus, and not, you actually use the other one. It's sort of a way to define, to actually construct vectors of words like thus, not, that, who.
The semantic one.
Yeah, it's semantics for some words which you don't want to, which are sort of logical, I don't know how they call them, logical words or,
Actions.
what do they call them?
They are actions. I mean, in this picture, you have both actions and cats.
Yeah.
Yes.
But the actions are not necessary for the grammatical derivation.
They are not necessary for the grammar, but they're very useful in the meaning. We build meaning vectors with them.
Well, I understand. But, so with your quantum stuff, you've got algebra and co-algebra mixed
Yeah.
together. But so are you saying the safe? If you don't have it, you don't need to do quantum stuff. So you're saying you've got co-algebra and linguistics also. That's what I don't
The main thing is like, well, it's actually Ruud and Steve mainly did this initially. Like they started to use this Frobenius algebra to model, for example, the word who. It just gives you the right behavior.
So you do need some.
You need them, yeah. It exactly gives you the right behavior if you model the word who by something which involves Frobenius algebra. You see the unit is sitting here you see the multiplication. It just gives you the right thing. You can sort of, like I said, you can solve an equation. Who is the man who Alice hates? You compute and you get what? If you model
I'm trying to understand why there's any reason whatever you say that it's for who. Okay.
what? Well, it's basically two proofs of concept. One, you just give some logical Boolean or whatever meaning to all your words and you compute. Second, you do experiments. with data sets and
Yeah,
whatever, and you get the better answers to this then.
No, I wasn't discussing the data set aspect, just,
Huh?
okay.
Right, I think it's time for everyone to get lunch unless we've got another burning question. So please thank Robert